Hello everyone. So today we're going to continue on 8.1. So last video we tried to talk about how to calculate work. So we basically divide into three different scenarios. The best case scenario would be right here, case 1, where the force is a constant force. It go in the same direction as the movement. So therefore you can simply just multiply the magnitude of the force times the distance traveled, and that gives you the amount of work being done. The second case is we're keeping the force constant, but it's just not in the direction of the movement. And we do have a fixed direction. And in this scenario, it's pretty easy fix. All we need to do is define the projection of the force, which will be in the direction of movement, and then multiply by distance traveled, and then we are still good to go. So now what's going to happen in case 3? Well, what if force is not constant and it changes directions? And also movement changes direction also. So what does that mean? So if a movement changes direction, that means the movement is a curve instead of a line. Oops. And if the force is not constant, also constantly changing direction, that will imply that we need to have some kind of meaning that the force is actually dependent on the position at the time. So what that would require would become something like this. Imagine that we have some kind of curve, and on that curve we sit an object, and this is where it starts. And then at this point you have a force, but as this object move along this path to different position, until we get to the end. At each of these positions, the force will be pointing in different direction. And somewhere here is where it's end. How do I calculate the amount of work being done in this case? So this, of course, being the most realistic scenario, where it gives us the most flexibility. The force can be changed or can stay the same. It doesn't matter. It can be different or can be the same. The object can move in a straight line or not in a straight line. It's perfectly okay. We just want to try to figure out how to calculate the work being done. So to do this, first we need to define. How do we find out what the force is at any given point? And also, how do we define this movement of this object? And of course, you probably already guessed what we're going to do. The force is actually going to be given by a function vector f of position vector x, which in this case, our function f map from Rn to Rn. Or if you picture this picture right here, would be R2 to R2. So the function f is position dependent. So depending on where the object is, that's how we know what kind of force it's experiencing. Okay? Then how about the curve? The curve will be given by the function g of t, where g go from R to Rn. So this parametrization of the curve could be anything. It could be a straight line, but could be a curve, could be a loop, could be anything we like. Okay? And in this case, we will define t to go between some number a to some number b, so that we have a beginning and end point. So now comes the big question. How are we actually going to calculate this? Well, we really can't, because so many things changing. But what we could do is not to calculate, but how about we try to estimate? So this is what I'm going to do. Okay. There you go. Now I copy the pictures. So imagine the following. Imagine that I don't know how to actually calculate this if the force keep changing the position, and also the curve, the object go in a curve. But what if we do the following? What if we imagine this? We imagine that at each of these positions, I can define a time variable. Let's say this is t sub 1. And let's say here is t sub 2. Let's say here is t sub 3. And then continue on down to t sub n as the last value, where t sub n is equal to b, t sub 1 is equal to a. And what if we pretend the following? We pretend that the direction when it goes from t sub 1 to t sub 2, for instance, instead of going through this curve, I'm going to assume that it goes through it in a straight line. Oops. Instead, I don't like the line, but okay, there you go. And I'm going to assume that that line kind of have, I'm going to use the tangent direction of this line, of this direction to connect them together. And then I can say go from here to here would be another straight line. And then let's say here to here is another straight line. And then from here to here would be another straight line. And then here to here would be a straight line. And then here to here would be a straight line. If I do that, I would actually turn this picture into this case, where I assume between each of these 2 points, we will assume the following. Assume between t sub k and t sub k plus 1, meaning between 2 consecutive points. We're going to assume between these 2 points, the force is constant. It doesn't change direction, and it doesn't change magnitude. And let's say that the movement is constant also, which in this case involve basically the velocity vector is fixed. So that we have a constant speed and a constant direction. It moves in a straight line. So if I assume those 2 things are true, we can actually try to estimate the amount of work being done by the following. We're going to assume that the constant force is given by this. That gives us the constant force. It doesn't have to go in the direction of movement, but at least we know that the force is constant. And we go define the direction to be based on the derivative. So that's the constant velocity vector. Oh, I need the velocity first. Velocity vector. Now with these 2 things, I can now try to estimate the amount of work being done. So I'm going to go and say work sub k, which is because that would be for the k between t sub k and t sub k plus 1. That would equal to, I do need to use, because remember in this scenario right here, we have a constant velocity vector, so a constant movement, a constant force, but they just don't go in the same direction. So based on what we learned in case 2, I need to do the dot product multiplied by the distance traveled. So here the dot product have to be the force, dot product the direction vector, but the direction vector has to be a normalized unit length vector. So we have to make sure that's the case. So let's do that. So therefore, in order to find the amount of work, it will be f of g of t sub k dot product. The normalized direction vector will be given by g prime of t sub k over the length of g prime of t sub k. So this part right here is the normalized direction vector. So this whole thing would give us the force or the projection of the force. So maybe write this way. So that is the projection of the force. Now I'm going to multiply that with distance traveled. So how do you calculate distance traveled? Simple. It's speed times time. So speed is given by g prime of t sub k, but the length of that multiplied by the amount of time it takes to travel between these 2 points, which would be the difference between t sub k and t sub k plus 1, which I am going to go and call that delta t sub k. So this right here is the speed, and this right here is the time. And so together, together this give the distance travel by this object. Notice what happened is that the speed actually cancel out. And if you think about it, it makes sense, because hopefully you remember learning from your physics teacher. So do your physics teacher proud. Hopefully you remember learning that in your physics class that the amount of work being done is actually independent on of speed. So no matter how quickly you travel that distance, or whether you travel extremely slow, it doesn't change the amount of work being done at all. If you want to take into account of how quickly you're doing those things, that I believe is referred to as power, not work. So which makes sense, because in this case, the math actually show that these two things, the speed actually cancel out. And therefore now our expression does no longer require the speed. And this gives us this expression, the work for sub k, or maybe I would write w sub k, is actually equal to vector f of g of t sub k dot product g prime of t sub k delta t sub k. So that gives us the amount of work, actually I'm going to say approximately equal to, because we assume quite a few things to calculate this. So that gives us the work between t sub k and t sub k plus 1. Now what we're going to do is, what if I want to find out the total amount of work being done? Well, then the total amount of work being done would be approximately equal to the summation k from 1 to n w sub k. When you add up all this work on each interval, then you have the total amount of work, which basically meaning that's approximately equal to summation k from 1 to n vector f of g of t sub k dot product g prime of t sub k delta t sub k. And I think some of you who are clever can see what we're working toward. So this gives us a total amount of work by breaking down this path into some finite number of points, and that many points. What if I want to get this estimate to be better? Well, simple. To make it better, I'm going to make more points on the curve so that I can form more intervals. The problem, the more interval we form, the smaller delta t sub k become. And eventually, when n go really large, delta t sub k go really small until it become almost like 0. And that's the essence of what a Riemann sum is that you try to add something that's infinitely many of them, but they all approach 0. And this sum then converge to what we call an integral. So in this case, I can now define the total amount of work being done is actually equal to the limit as n go to infinity, summation k from 1 to n, vector f of g of t sub k dot g prime of t sub k delta t sub k. And this is a Riemann sum. And we know what the Riemann sum actually converges to. It converges to an integral. So in this case, I can now define that this is work for the vector, for the force V along a curve g of t from A to B is given by this integral. So therefore indicate that the amount of the numerical value that we have been calculating is actually just called work. That's all that is. So the most basic interpretation of what a line integral is, it would be to refer to as calculating amount of work being done. Now, here comes the tricky part. When it comes to line integral, there are actually multiple ways to represent what a line integral is. There are actually 3 different expressions that all create what we call the line integral. Now, I know what you're probably thinking is, then why do we need to have 3 different notations for this one thing? Well, simple. The answer is to confuse students. That way, make it harder for them to learn and therefore make it feel smarter when you learn it. Now, all joking aside, why is it has to have 3 different notation? Because of the way you use them. Okay, show you. So our first notation is this one, which is our the first introduction to what a line integral is to all of you. And this is perfect. So in this case, use this if you are given the parameterization of the curve, which is g of t. So you have g of t. This is probably the default mode that you want, default formula you want to use. What else could you be given? Well, how about something like this? Let's say you're given a curve alpha with parameterization g of t. Let's say t go from A to B. Then the line integral can also be written this way. Oops. So this formula actually, in a sense, kind of explain what we are doing. See, the first one is more like when you use it to evaluate a line integral. This one is more like you use it to describe what you try to do. So this is, technically speaking, not a definite integral, and you'll see why. There will be an integral over alpha vector f dot vector t ds. Notice that this notation is more similar to the Riemann integral, where you define the regions of integration directly underneath the integral symbol. In this case, our region of integration is the curve alpha. And then we have the integrand. Okay, now because this is a single integral, our differential is actually ds. So what is ds? Well, let's talk about it. So in here, obviously, f is our quote-unquote force. So what is vector t and what is ds? Vector t is what we call the unit tangent vector. Basically defined to be g prime of t over absolute value of g prime of t. So that, technically speaking, is the direction of movement at any given point. What is ds? ds is often referred to as an odd length differential, usually referred to as like a portion of a curve, and is given by this expression, length of g prime of t dt. So this expression kind of tells us what we are actually doing. We are taking the projection of f, which is why we do f dot product, the unit tangent vector, and then multiply by a small line segment, a small part of the curve that represents the distance that travel. And then when we use the summation to add them up throughout the entire curve alpha, we'll get our line integral. So that's how you read this example. The integral is like adding over the entire curve, that's why the alpha is on the bottom, the projection of f onto the direction of movement multiplied by short lines, a short part of the curve. So this expression kind of explains what is a line integral. And it makes more sense when you see this expression and you know what it's trying to tell you to do. While when you try to evaluate, you actually have to use the formula number 1. Notice that both 2 and 1 require the parameterization. So therefore, most likely you'll be using the Riemann integral, or like the second notation right here, to describe what you're trying to do. And then you rewrite that into number 1 so they can actually evaluate the line integral. 3 is a little different. And it's probably the most straightforward way to kind of identify what is the line integral. So this is actually what you see me use a lot, as well as what the textbook use a lot. Let's say we're given a curve, alpha, in Rn. We don't know the parameterization, but we just know there's a curve. Let's stand the line integral of vector f along this curve alpha is given by the formula integral over alpha vector f dot d vector x. This is it. So that is probably the most straightforward way to represent the line integral, because they have the least amount of writing. You know, and as you know, mathematicians hate to write. And let's try to explain what do we have here. So in here, what is dx? D vector x is a vector in Rn, and kind of like the derivative or the differential of vector x. And so how does that work? Well, let's say vector x is x1, x2, dot, 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 to xn. Then d vector x will just simply equal to dx1, dx2, dot, 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 to dxn. Notice there's no that did not identify the independent variable. And in this case, we don't know what the independent variable is yet. Okay? But in this scenario, we are actually treating that this integral has an independent variable, x1 to xn. By far, this would probably be the most hardest to use. But in this case, you basically just giving a curve in Rn. You don't have a parameterization of this curve. And you will try to do the problem without the parameterization. And depending on how you define the curve, it could be easier or could be more difficult. Really depends. So let's show you how to do some of these different type of problem, okay? So the problem will now be written this way instead. Instead of me kind of spell it out, the word, find the line integral of f along alpha, blah, 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 blah. I'm now just going to give you symbolically what it is. So meaning something like this. Let's say given the function vector f of x, y, z is equal to, let's say, x minus y, y minus z, z minus x. And let's say we're going to let alpha be the curve given by And I'm going to give you a parameterization of it. And let's just do a very simple parameterization, just like the curve we had before. And now I'm going to just ask you to find me this. So that basically meaning find me the line integral of f over the curve alpha. So how do we actually proceed? Well, actually pretty simple. This is how we proceed. We just go do exactly what this thing say. Integral of alpha vector f dot d vector x. In this case, because we are in R3, I have vector x to be x minus y, y minus z, z minus x. Dot product d vector x, in this case in vector x is x, y, z, d vector x will be dx, dy, dz. And now this come out to be something extremely interesting that I want to point out. So if I do multiply this dot product, what I have is a line integral over alpha of x minus y dx plus y minus z dy plus z minus x dz. Here's a very common mistake. You cannot split this into 3 separate integral. The reason why you cannot do that, because the curve alpha changes all x, y, and z together. And so you cannot separate them into 3 separate integral, one for dx, one for dy, one for dz. That does not work. 2. Notice that this have 3 differential, dx, dy, and dz. But it's not a triple iterated integral or triple Riemann integral. Notice that those dx, dy, and dz are not multiplied together. If they're multiplied together, then that would form a triple differential that will require a triple integral to do. But here, dx, dy, dz are actually combined together through addition. Therefore, this is not a triple integral. And you also cannot separate them because all 3 variables are actually changing at the same time. So how are we proceed with this problem? So that is probably one of the most important thing you need to understand about line integral. Is that line integral is a single integral, but it could be a single integral that travel through higher dimension, like in this case, travel through R3. So the problem is there's a mismatch of dimension. A line integral is a single integral because you're integrating over a line which is one-dimensional. But that one-dimensional object travels through, in this case, 3-dimensional space. Therefore, it's changing 3 different coordinates at the same time while we travel along this curve. And the problem, a single integral cannot really deal with 3 different changing variables. In this case, 3 different differential, dx, dy, and dz. Therefore, we now need to have a way to calculate this integral. And the main idea is to try to change it into a single variable integral. Meaning we have to now relate dx, dy, and dz all together into one single variable. And we have that, which is right here. We know that g of t is t squared, t to the third. Imply x is t, y is t squared, z is t to the third. And therefore allow me to say dx is equal to dt. dy is equal to 2t dt. dz is equal to 3t squared dt. And now I'm ready to convert my integral of x, y, z with dx, dy, dz into one single parameter, which is t. So now I can say that this integral is from 0 to 1, because that's what t go travel through. X minus y become t minus t squared dx, which is dt, plus y, which is t squared minus t to the third. dy would be 2t dt plus z, which is t to the third, minus x, which is t, times 3t squared dt. So now notice that there's no more x, y, and z, they're all t. So now I can actually combine everything together. So if I do that correctly, that would be t minus t squared plus 2t to the third minus 2t to the fourth plus 3t to the fifth minus 3t to the third all over dt. So if I look at this correctly, I can actually cancel the 2 to just 1t to the third. And I can easily integrate this. So this is 1/2 t squared minus 1/3 t to the third minus 1/4 t to the fourth minus 2/5 t to the fifth plus 3/6 t to the sixth, which is technically 1/2. And we evaluate from 0 to 1, so that's just basically 1/2 minus 1/3 minus 1/4 minus 2/3 plus 1/2. So 2, 3, 4, 5. The least common denominator, I believe, is 60. So that's 30 minus 20 minus 15 plus minus 24. Plus 30 again, so 60 minus 59, so therefore it's 1. So it's 1 over 60. Alright, unfortunately my video went over 30 minutes, I apologize, so we'll continue on our next video. Alright, talk to you guys in the next video, bye bye.